Chemistry time.
Hello there and welcome back to Chemistry Time. In today's discussion, we are going to take a closer look at some important reactions that often occur in solutions. We are going to be focusing on the concentration of a solution, neutralization reactions, and oxidation reduction reactions. When considering aqueous reactions, the way we measure the amounts of each substance is different from those that occur in other states of matter. Since a solution consists of a solute dissolved in a solvent, such as water, we need a way to measure the total amount of solute that is available to react. We do this using molarity, which is calculated as the moles of the solute divided by the total volume in liters of solution. In this way, if we know the volume of a solution along with the molarity of that solution, we can determine the moles of solute present. A common procedure that is used to adjust or alter the concentration of a solution is dilution, which involves adding solvent to decrease the overall concentration. We can calculate the new concentration of this diluted solution by using the following equation. The initial molarity times the initial volume is equal to the final molarity times the final volume. If we initially had 1 liter of a 0.5 molar salt solution and we diluted the solution to a total volume of 2.5 liters, we can find the concentration of the final solution. When we rearrange this equation to solve for M2, we find that the final concentration of salt is 0.2 molar. One type of reaction where these types of calculations are common are neutralization reaction, which is where an acid and base react to produce a neutral salt in water. In these types of reactions, it is often necessary to determine how much of an acid or base solution is needed to neutralize the solution. For example, what volume of 0.5 molar sodium hydroxide is needed to neutralize 250 milliliters of a 3 molar hydrochloric acid solution. Just like with normal stoichiometric calculations, we need to start off by writing the balanced chemical equation where hydrochloric acid reacts with sodium hydroxide to form sodium chloride in water. In this balanced equation, all the coefficients are 1. We then need to calculate the total moles of hydrochloric acid, and we do this by multiplying the molarity by the volume of the solution to find the moles of hydrochloric acid. We also know that the ratio of HCl to NaOH is 1:1. We also know that our sodium hydroxide has a concentration of 0.5 moles per liter. Therefore, we would need 1.5 liters to neutralize this solution. Another important technique regarding neutralization reaction is titration, in which a base with known concentration is added slowly to an acid of unknown concentration. The volume of base solution needed to neutralize the acid will then allow us to calculate the concentration of the unknown acid. One important observation about neutralization reactions is that some substances that undergo these reactions produce unstable products, which decompose into a gas. Some examples of these substances are carbonates and sulfites. When carbonates are neutralized, they form carbonic acid, which immediately breaks down into carbon dioxide and water. Sulfites tend to form sulfurous acid, which will immediately break down to form sulfur dioxide and water. The last type of reaction that we are going to discuss are oxidation reduction reactions, also known as redox reactions. These reactions involve the transfer of electrons from one substance to another. The substance that loses electrons is said to be oxidized, while the substance that gains electrons are said to be reduced. You can use the mnemonic oil rig to remember this, which stands for oxidation is losing, reduction is gaining, and this is in reference to electrons. Some other important terminology is the oxidizing agent, which is the substance that undergoes reduction, and the reducing agent, which undergoes oxidation. There are several rules regarding oxidation states, which are fictitious values that are assigned to observe the transfer of electrons. Oxidation states follow a hierarchy of steps that need to be followed in this order. First, every pure element, including diatomic elements, has an oxidation state of 0. The oxidation state of an ion is given by its charge. When fluorine is present in a compound, it is assumed to have an oxidation state of -1. Group 1 and 2 have an oxidation number of +1 and +2 respectively. Hydrogen usually has a +1 oxidation state in covalent molecules and a -1 state in ionic compounds with metals. The oxidation state of oxygen is often -2, but can sometimes vary depending on the molecule. Followed by group 7A, which typically has a -1 oxidation state, but can vary depending on the other atoms, not including fluorine. Finally, the total oxidation state of a compound is equal to the sum of the individual oxidation states of each element. These rules allow us to calculate the oxidation states of each atom in a molecule. For example, if we look at phosphoric acid, which is a neutral molecule, we know that we have 3 hydrogens with an oxidation state of +1, and each oxygen will have an oxidation state of -2. That means for the overall oxidation state of phosphoric acid to be neutral, the phosphorus atom must have an oxidation state of +5. We can also use these rules to determine when a redox reaction occurs. For example, when calcium reacts with fluorine gas, it produces calcium fluoride salt. This is a redox reaction because calcium and fluorine initially have a charge of 0, but in the product they have charges of +2 and -1 respectively. This means calcium has been oxidized because it lost electrons while fluorine was reduced. Many reactions such as synthesis, decomposition, single replacement, and combustion reactions can often be classified as redox reactions. These reactions can be broken down into individual steps that show these transfers of electrons. If we return to our previous example, we could show the oxidation of calcium as calcium releasing 2 electrons and forming an ion. The reduction of fluorine gas would be shown as fluorine accepting 2 electrons to form 2 fluoride ions. When we combine these 2 steps, we see that there are the same number of electrons on each side of the balance equation, which will then cancel out, giving us the overall balanced redox reaction. Another way to determine whether an element will be oxidized or reduced is to use an activity series, like the one shown here. Elements at the top of this series are likely to undergo oxidation, while elements toward the bottom are less likely to be oxidized. Today's discussion contained a lot of important information regarding solutions, acid-base neutralization, and redox reactions. We also learned how to determine which species are oxidized and reduced, and how to determine the oxidation state of atoms in a compound. Thank you for joining me on Chemist Tea Time, and have a wonderful day. Thank you, and charge on.